Hi and welcome to this video on equatorial celestial coordinates. So what I'm going to cover here is the definition, what do we mean by equatorial celestial coordinates, how we get from equatorial celestial coordinates on a star chart to the actual position in the sky of an object, how the coordinates of objects such as the sun, the planet and other solar system objects change over time, and how the coordinates of stars change over time. These are the standard coordinates used on star charts, found both in books and on the internet. For example, here shows the area of sky around the constellation Ursa Major, the Great Bear. The 7 stars, which I've circled in red, form an asterism called the Plough or the Big Dipper. Ancient Greek astronomers believed the Earth was at the centre of the universe, was a fixed sphere of stars which rotated once a day, and this was the accepted view of the cosmos until the 16th century. Even though we don't believe the Earth is at the centre of the universe, the basis of the coordinate system is the celestial sphere. That's an imaginary sphere with the Earth at its centre, which lies a great distance from Earth. So this diagram isn't to scale at all. The Earth would actually be a tiny dot with a celestial sphere wrapped around it. And because of the vast distances of the stars, they're effectively fixed on the celestial sphere. The North Celestial Pole is an imaginary point in the sky. It's a projection of the Earth's North Pole onto the celestial sphere. Lines of declination are a little bit like lines of latitude on Earth, and lines of right ascension are a little bit like lines of longitude. The 0 point with declination 0 and right ascension 0 is the vernal equinox, which lies in the constellation Pisces. The North Celestial Pole has a declination of 90 degrees and the South Celestial Pole has a declination of -90. The Earth rotates once every 23 hours, 54 minutes and 4 seconds, and that period of time is known as a sidereal day and is slightly shorter than the 24-hour day, which is based upon the rising and setting of the sun. If we were to stand at the North Pole, in the winter months obviously, when it's completely dark, and look up in the sky, we see that all the stars moved in perfect circles around the North Celestial Pole, and it would take one sidereal day to complete a complete circle. The lower the declinations, the larger the circles and the lower in the sky. If we go to a lower latitude, such as 50 degrees north, so that's just a little bit north of Vancouver, then we can see that stars once again rotate around the North Celestial Pole, which is actually near the very bright star Polaris in the constellation Ursa Minor, the Small Bear. But this time, stars rise and set. Okay, let's look in the detail in the path of a star having declination 35 degrees in a place with latitude of 45 degrees. You see the star rises in the east, moves higher in the sky, reaches its highest point when it crosses the meridian, which is an imaginary circle joining the zenith, the highest point in the sky, to the north and south directions. It then descends and finally sets in the west. If we look again at another star, but this time declination 0 on the celestial equator, it follows a similar path, but it doesn't get as high in the sky and isn't above the horizon for a short amount, isn't above the horizon for so long. So what we want to do is to work out a star's position in the sky. We want to know its azimuth, which is its angle from the northerly direction, and its elevation, sometimes called altitude, which is an angle above the ground. Or to put it another way, how do we get from the diagram on the left to the diagram on the right? Now, today, most serious-ish amateurs astronomers have a telescope on a go-to mount, and this does all the calculations for you, going from the equatorial coordinates to position on the sky. You can even buy a smart telescope for £600, which has a whole database of stars behind it, as well as working out where the telescope needs to point. But despite all this technology, it's still interesting to think about how we go from the position on a star chart to an actual position in the sky. The Earth takes 23 hours 56 minutes roughly to make a complete rotation on its axis, but the solar day is on average 24 hours long. And this is because during the time it's performed one rotation, the Earth has moved a little around the Sun in its orbit. For example, if we take the point in time where the Sun is its highest in the sky and mark it with a purple dot, one rotation later, because the Earth has moved in its orbit a bit, the Sun isn't quite overhead at this point. It takes a further 4 minutes for the Earth to rotate a little further to reach this point again. We call the time taken for the Earth to rotate once on its axis a sidereal day. A sidereal day is divided into sidereal hours, minutes and seconds, and all of these are slightly shorter than our normal day of hours, minutes and seconds. Sidereal time at a given location on Earth is called the local sidereal time, and the local sidereal time, or local sidereal day rather, begins when the vernal equinox, that's the point in the sky with 0 right ascension, 0 declination, crosses the meridian. All places at the same longitude have the same local sidereal time. Because the sidereal day is roughly 4 minutes shorter than the civil day, the difference between civil time we use for our daily timekeeping and local sidereal time, LST, advances by about 4 minutes a day, as these examples for Manchester in England show. The next thing we need to look at is the hour angle. This is the elapsed sidereal time since a star crossed the meridian, and it can be expressed either as a time, hours, minutes and seconds, or by multiplying by the value by 15 in degrees. When it crosses the meridian, the hour angle of an object is 0, and as time passes, as the Earth rotates, it increases. So, let's look at how the elevation of a star changes over a sidereal day. Starting at hour angle 0 when it's its highest, between 0 and 12 hours, hour angle, the object sinks lower and reaches lowest elevation at an hour angle of 12. It then rises, reaching its highest elevation back at an hour angle of 0. Hour angles of greater than 12 hours are often, in fact usually, expressed as a value subtracted from 24. So instead of saying an hour angle of 21 hours, we say an hour angle of -3 hours. Instead of an hour angle of 22:30, we say an hour angle of minus 1 hour 30. The hour angle is simply the local sidereal time minus the right ascension. So for any star with 0 right ascension, the hour angle is simply equal to the local sidereal time. So now we've got hour angle out of the way, we can explain how we get from hour angle and declination coordinates to azimuth and elevation. Essentially, what we're doing is a transformation from one set of coordinates on a sphere to a different set of coordinates. And I've put the formula to do it here. If you want to see how this formula is derived, then just have a look at my blog page. The final thing I need to mention is the speed of light in air is slightly lower than it is in the vacuum of space. And this means that as light from a star or any object outside the Earth's atmosphere comes into the atmosphere, it's bent by refraction, and this causes the elevation of a star to be slightly greater than the calculated elevation. In this diagram, the effect has been greatly exaggerated. As you'll see next, the change in elevation due to refraction is very small. The actual amount of bending is complicated to calculate and depends on the composition of the atmosphere, and the formula I've given here is only an approximation. This table shows the change in elevation in arc minutes, where 1 arc minute is a 60th of a degree. And because this effect is so small, I'm going to ignore it for the time being. So using this formula, let's work out the minimum declination of a circumpolar object. That's an object which never sets, it's always above the horizon. Well, the object is at its lowest elevation at 180 degrees, when it just hits elevation 0. We know our latitude, so we just want to find out the declination. So putting these numbers into the formula, we get 0 equals sine dec times sine lat minus cos dec times cos lat. And we know from high school that cos dec plus lat equals cos dec cos lat minus sine dec sine lat. So the cosine of 90 degrees is 0, so dec plus lat equals 90 degrees. So the minimum declination is the latitude subtracted from 90 degrees. The effect of the Earth's atmosphere is to reduce the amount of light getting to an observer at low elevations, because the light has to pass through more atmosphere. And for that reason, it might be worth rerunning the calculation we've just done to find the minimum declination an object would need to be never to drop below 3 degrees above the horizon, so it was clearly visible. In this case, the minimum declination is 93 degrees minus the observer's latitude. Another thing we can work out is the maximum elevation for a given latitude and declination. I've put the working out here, and I'll just pause the video a bit for you to have a look at it. As you can see, the maximum elevation is the inverse sine of the cosine of the declination minus the latitude. Objects with a declination of the latitude minus 90 degrees reach a maximum elevation of 0, so they just touch the horizon. Objects with a lower declination than this will never rise. So for Manchester, England, which has a latitude of 53.5 degrees, any object with a declination more south than 36.5 degrees will never rise above the horizon. And here's an example of using these formula for places at different latitudes. As you can see, as you go down to lower latitudes, less and less of the sky is circumpolar, but at the same time, the portion of the sky where objects never rise at all also gets smaller. I'll talk now about the extreme cases of the North Pole and the equator. An observer at the equator will see anything at the North Celestial Pole, or indeed the South Celestial Pole, completely stationary, sitting on the horizon, neither rising nor setting. Every other object rises in the east and sets in the west, as you can see by the red dotted lines. The blue dotted line is the celestial equator. The entire celestial sphere is visible, and all objects are above the horizon for 12 hours and below the horizon for 12 hours. Of course, objects very close to the horizon are difficult to see because of the amount of atmosphere they have to pass through. If we go to the other extreme, to the North Pole, then anything at the North Celestial Pole itself is completely motionless and is directly overhead. All objects move in circles, keeping constant elevation, never rising, never setting. Only the northern half of the celestial sphere can be seen. Objects with a declination above 0 never set. The southern celestial sphere, that's declinations having declinations below 0, never rise.